Okay, let's dive right into this explainer. We're going to explore the frankly fascinating, rapid evolution of long context language models. We're literally living through a fundamental shift in how artificial intelligence processes information. We've gone from models that could barely remember a single paragraph to systems capable of swallowing entire libraries whole in an instant. It's an absolute engineering marvel, and it's completely reshaping our relationship with data.
Just think about that for a second. Seriously, how do we condense 60 hours of human reading into mere minutes of AI processing? As biological creatures, you and I, we're bound by localized serial reading, right? We have to read one word, one page, one book at a time. But what actually happens when we shatter that biological limit? What happens when we engineer a system that ingests and understands hundreds of thousands of words simultaneously?
Well, to really get why this is so huge, we have to look at humanity's historic, manual struggle with processing vast amounts of data. In 300 BCE, librarians at the Library of Alexandria had to painstakingly, manually copy and compile catalogs just to manage ancient texts. Fast forward to the 800s, astronomical officials in the Tang dynasty were manually calculating vast arrays of seasonal data. Then in the 1400s, typesetters are meticulously arranging enormous printing plates. And even into the 1900s, modern scholars were forced to examine dozens of documents by hand to understand a single subject. The point is, throughout our entire history, the ultimate bottleneck has always been our capacity to manually process information.
But that bottleneck, it's officially breaking. Let's look at the sheer scale of this revolution. Early language models were strictly limited. They could process a few dozen, maybe a few thousand tokens at most. And think of a token basically as a fragment of a word. So early models were fine for a short conversation or summarizing a quick article. But contrast that with modern long context language models, or LCLMs. Today we're seeing context windows stretching to 128,000, a million, and even up to 10 million tokens in just a few short years. The growth is just absolutely astronomical. To put those abstract numbers into perspective, the source material phrases it perfectly. It says, this scale allows for the single-pass ingestion of Tolstoyan-scale narratives, 560,000 words, effectively condensing 60 hours of human reading into minutes. Just imagine that. Imagine dropping the entirety of War and Peace into a prompt, and the model instantly holds every single character, every plotline, and every thematic nuance in its working memory, all at once. It's wild.
So, here's our roadmap for today's explainer. First, the context length revolution. Second, training with better data. Third, mapping words in long text. Fourth, solving the attention bottleneck. And finally, applications and the future.
Let's start with part 2, training with better data, the fuel. You simply cannot train a behemoth language model without the absolute highest quality fuel. The crucial point here is that engineers have to carefully curate, mix, and even synthesize data to maintain the model's proficiency across all lengths. You can't just throw raw web pages at it and hope for the best. First, they use data filtering. Engineers apply complex heuristic rules and analyze self-attention patterns to identify texts that have really strong long-range dependencies. Second, data mixture. It turns out that oversampling lengthy sequences, like long books or massive code repositories, and then blending them with high-quality short context is super vital. And finally, because naturally occurring long context data is actually pretty rare on the open internet, they use data synthesis. They literally pack and cluster semantically related shorter texts into a single massive context window. This basically teaches the model how to connect the dots across massive distances.
Moving on to our next section, mapping words in long text. The map.
Okay, so once you have the data, how does the model actually navigate it? I mean, ask yourself, how does a model remember the exact location of a single word inside a 560,000-word book? Well, the answer lies in position embedding. By default, the transformer architecture, which is the foundation of these models, processes everything at once in parallel. It doesn't read left to right like we do. It basically just sees a giant bag of words. So position embedding is this incredibly clever mathematical mechanism that injects spatial and sequential information right into the data. It gives every single token a precise set of coordinates so the model knows exactly what order the words appear in.
And what's really interesting is how we've evolved our map-making over time. We started with absolute position embeddings, which just assign fixed coordinates to exact positions. Pretty straightforward. But today, the industry has heavily shifted toward relative position embeddings, specifically a technique called Rotary Position Embedding, or RoPE. RoPE rotates the mathematical representation of words based on their absolute positions. This means the model naturally focuses on the relative distance between words, which is a huge deal. It's actually become the most pervasive strategy in modern AI. Oh, and there are also emerging content-aware embeddings that actually adjust positional information based on the semantic meaning of the text itself, which is just mind-blowing. But, what happens when you want to feed the model a text that's way longer than anything it actually saw during training? Well, you have to extrapolate. Engineers essentially use two main tricks to stretch a model's context window, all without having to spend millions of dollars retraining it from scratch. The first trick is position reorganization. This is where the model reuses existing, well-trained relative position indices for much more distant tokens. The second trick is position interpolation. Think of this one like taking a really long ruler and uniformly shrinking the physical distance between the inch marks so that a much longer measurement fits onto that exact same physical ruler. It monotonically reduces all input token positions to fit perfectly within the model's original trained limits.
Next up, solving the attention bottleneck, the engine.
Let's see how all this builds into the biggest hurdle of all, computational limits. We have the fuel, we have the map, but now we really need to look at the engine. This right here is the mathematical villain of our story, O of n squared, otherwise known as quadratic complexity. In a standard transformer model, every single word has to compute into tension score with every other word in the sequence. So if you double the text length, the computation doesn't just double, it quadruples. If you jump from a few thousand words to a million words, the computational cost and the memory required absolutely explode.
So, to stop computers from literally melting down, engineers developed sparse attention. Think of standard attention like a massive floodlight that illuminates every single word equally. Sparse attention, on the other hand, acts like a highly focused spotlight. Here's how it works. First, it identifies only the most absolutely important tokens. Second, it ruthlessly evicts unnecessary data from the model's short-term memory, which engineers call the KV cache. And finally, it processes the remaining, highly relevant sequence with extreme efficiency.
And the engineering marvels they've built to actually achieve this are just stunning. They dynamically trick the system to save memory while keeping accuracy incredibly high. Take streaming LMM, for instance. It figures out that early tokens act sort of like attention sinks, and it actively holds on to them to keep the model stable over practically infinite links. Then you have H2O. This strategy dynamically drops tokens, keeping only the heavy hitters, the ones that have the absolute highest attention scores. Pyramid KV takes a totally different approach. And notice that language models act kind of like a funnel, so it dynamically allocates way more memory to the lower layers of the model and heavily restricts memory at the top layers. Finally, there's duo attention. It literally splits the model's attention heads. It forces some to hold full memories for retrieving facts, while others operate on strict fixed-size memory budgets. Honestly, it's just incredibly clever resource management.
Which brings us to our final section, applications and the future.
So we've covered the data, the architecture, and the memory optimization. But why does all this incredible under-the-hood engineering actually matter to us in the real world? Well, this single-pass ingestion capability is totally transforming how we interact with generative AI. Because these models now have a massive internal workspace, they can perform O1-like long reasoning. They can explore, reflect, and backtrack their own logic all within a single prompt. It also enables complex agent workflows where AI acts autonomously over long periods. In information retrieval, you don't even need to summarize documents first anymore, you just feed the whole database right in. Developers can literally drop an entire massive codebase into a prompt for instant debugging. And it unlocks advanced multimodal intelligence, processing thousands of images and hours of video seamlessly.
Which leaves us with this final profound thought. For thousands of years, humanity's progress was bottlenecked by our biological limits to read and synthesize information serially. But we've just built an engine that completely removes that limit. So what happens to human learning, discovery, and innovation when an AI can perfectly reason through an infinite context window? The context length revolution isn't just about fitting more words into a prompt. It's about fundamentally expanding the horizon of what machines can understand. Thank you so much for joining me on this explainer. Keep exploring, and I'll see you next time.